Okay, so first let's talk about exponential functions. Okay, what do I mean when I say exponential function? I'm talking about this. A number raised to the x power. That is an exponential function. Okay. A is going to be a positive number that is not 1. Okay. And x can be any real number. Okay, we're going to stick with real numbers. Okay, we just got done working with polynomials, so please look at the difference. X cubed is a polynomial. 3 to the x would be an exponential function. We need to be able to recognize the difference, okay? Okay. So what you're going to notice is your variable, x, is going to be in your exponent as opposed to being the base. Okay, so we're going to talk about the general shape of an exponential function. Depending on what the base is, it will increase faster or slower, okay? But they're all going to have the same general shape, okay? Anytime we have f of x equals a to the x, this is what it's going to look like. We will have a y-intercept at 0, 1. Because anything raised to the 0 power is 1. Okay. And I have this red dotted line right here. You see that? What do we call that? It's an asymptote. Y equals 0 will always be, will be your asymptote when you have a to the x. We cannot take a number, a positive number, raise it to a power, and get a negative number. Anytime we raise a number to a power, we're going to get a positive value out of it because a is a positive number. Okay, a to the negative 1/2, a to the 100, a to the negative 20, they're all going to be positive values. Okay, so that horizontal asymptote is saying, hey, we can't have anything below here. Okay, we can't even have 0. That's why we have the asymptote there. Okay, so if this is our graph, all right, our domain, what kind of x values can we plug in? We can plug all of them in. Okay, we talked about we have a y-intercept of 0, 1. Okay, our range. Okay, our range. I want you to think about where do we have y values? Okay, where do we have y values? Okay, Sydney, where are our y values?
Anything above 0.
Yeah, anything above 0. And we have that asymptote there. They're approaching. So we have 0 to infinity where we don't include 0. Okay. Increasing, we are always going to have an increasing function. In this case, we call this exponential growth, right? You might talk about that in your science class. Yes? Exponential growth? And this function doesn't decrease. The only thing that's going to change is how fast this grows. If we have 2 to the x compared to 10 to the x, they're just going to grow, one's going to grow a little faster than the other. Okay. Now, have a discussion with your pod. Just take like 15 seconds. If I change that to a to the negative x, what's going to happen? Talk about it first. All right, pod 1, what's going to happen?
It's going to start decreasing.
It's going to decrease. A to the x, here's a to the negative x. We like to call this exponential decay. All right, because our exponent, which we like to think of as our rate, is negative. All right, so every other feature about the graph stays the same. We have that horizontal asymptote. We have that y-intercept of 0, 1. Okay, but now we're decreasing instead of increasing. Okay, that's the only thing that changes. So as a reminder, these are problems I'm going to ask you to do without a calculator, okay? And your quiz will be a few questions with the calculator, a few questions without a calculator, okay? Same thing with your test. You'll have like 2 different parts. Okay. I guess we can talk about this. Everything's going to stay the same, except we're going to decrease instead of increase. So we are a class of, what are we, like 27, 28 of us? We all come from different Algebra 2 teachers, okay? So how your Algebra 2 teacher, whatever their expectations were for graphing these may be different than mine, okay? But this is the minimum what I would like to see, okay? So if we have a function, 3 to the x, okay? This is what we call a parent function because we haven't like added anything to it, subtracted anything, multiplied anything to it. Okay, this is our parent function. What I'd like to see is that you draw and label your asymptote, and that you think about these 3 coordinates. When x is 0, -1, and 1. Okay? Well, I already told you that when you plug in 0, what do you get? 1. Our y-intercept is 0, 1. Okay? When we plug in 1, what's 3 to the first power? 3. Okay? And then what's 3 to the negative first power? 1/3. Okay? Those coordinates are the easiest 3 to think about because you really don't have to do any calculation. Okay? And they're going to be graphable, right? If I ask you to plug in x is 2, depending on what your base is, that could be off the chart. Okay? So these 3, we don't have to think too hard about their calculation. We have kind of a pattern going on here. We're always going to be able to graph them. Now, this is all fine and dandy, but do you really think I'm going to ask you to graph a to the x? Okay? Probably going to ask you for something a little bit more detailed than that. So, take a moment and talk about what a, h, and k do to your function. Take a moment in your pod. What can a, h, and k do to our function? All right, let's talk all together. Gabe, what did Pod 6 talk about as far as A is concerned?
It will cause stretches.
What kind of stretches? Vertical or horizontal?
So, horizontal. Now let's here. Do you have a corner?
You can consult your neighbor. Vertical or
We don't know.
okay. Well, you said it's outside. What does K affect the horizontal or vertical? Vertical. So A, since it's on the outside, is also going to affect vertical. So you said stretch or shrink? Okay. What about if A is negative? If A is negative, Kinley, what happens? Okay, the graph would flip upside down. Very good. If we have a negative A, we would reflect, right? I just don't want you to forget that. All right. H. Emily R., what is H going to affect?
Send it a little bit right or left.
Okay. Right or left shift. Good. And then K. Oh,
Mr. Glover.
this is Miss Holman. Good. How are you? Nope, I do not. No, this is my class, yes. I am B21. Okay. So K. Okay. All right, Nate, what is K going to do to our graph?
Move it up or down.
Okay, so this is what I want you to think about. I want you to think about the parent graph. And from the parent graph, we are going to take these three coordinates and shift them or stretch them or reflect them, whatever A, H, and K tell us to do. All right? For example, please write down 3 raised to the x plus 1 power. Okay, so our parent function is 3 to the x power. And to be very truthful, some of you are not going to have to write this down. Some of you really like to write this down. Okay, so with our parent function, I want to think about these 3 coordinates. -1, 1/3, 0, 1, and 1, 3. Those are the 3 coordinates I want you to think about for the parent function. Now, let's talk about what this is doing right here. That +1, that's attached to the x inside of our function. Okay? That is affecting the graph in what way? Emma Ralston, what do you think?
Or up and down.
Okay, Emma's asking, is it shifting left or right? Or up and down? Okay. Emma, stop. Where is the plus 1, inside or outside?
Inside,
So what would you tell Emma Ross?
and shift it left and right.
Okay, it would shift it left and right. So which way, Emma Ross? So this is a shift 1 to the left. How do we feel about that? Shift 1 left. Okay. So 3x to the x plus 1, we're going to take these coordinates and shift them left 1. So negative 1 1/3 is going to shift left 1 to negative 2 1/3. 0 1 is going to shift to the left, and it's going to be negative 1 1. 1 3 is going to shift to the left 1, and it becomes 0 3. Okay. Our asymptote is not affected because we had a horizontal shift. So it remains at y equals 0. And there is our new graph. Riley, how would you describe the domain?
All real numbers. Oh, sorry. I didn't know.
Oh, dang it. Sorry. There's too many double names in here. We have 2 Emmas, we have 2 Rileys, and we have 2 Emilys. That's it, right? Those are only double names? What? Yes. But you go by Addie, you go by Addison, right?
I go by you.
You go by Edgar. Okay, so 4 double names. It's very stressful for me. Okay, so Riley, stop. How would you describe the range?
0 to negative.
Good. Okay. If you have an exponential function, your domain is always all real numbers. Okay. Now, let's talk about this graph, 3 to the x minus 2.
So just keep
Okay. Monique, you were really excited about this one. Can you tell the class what is that minus 2 doing?
He's gonna bring it down to. Down.
Okay. So when we think about our parent function, and I know you already have this written down, but in case you want to actually go through the process of writing it down in your work, okay, when we think about the parent function, we think about negative 1, 0, 1. So we'd have negative 1 1/3, 0, 1, and 1 3. Obviously, those y values are going to change if your base is something that's not 3, right? If you had 10 to the x, you would have 1/10, 1 and 10. If you had 7 to the x, you'd have 1/7, 1 and 7, right? So when we talk about 3 to the x minus 2, that 2 is after our function, so it's affecting it vertically. We're just going to take these coordinates and shift them down 2. We'll start over here with 1, 3. If I have the coordinate 1, 3 and I shift it down 2, we're at 1, 1. I would literally put it on your graph and count it. Okay? We have the coordinate 0, 1, and if I shift it down 2, we're at the coordinate 0, negative 1. Okay? Negative 1 1/3, and I shift it down 2. What is that? Okay. Negative 1 2/3 would be an appropriate. This is like the one time I will let you use mixed numbers. I usually hate mixed numbers, but I will let you use them in your XY chart. Okay. I wrote that on the wrong spot. I'm very sorry. I know. I am sorry. if you're somebody who is more of a number thinker, since we went down 2, that means we subtracted 2 from our y's. So all of these y values we subtracted 2 from for these y values. Okay? If you like to think of it more that way, there you go. If you like to think of it graphically, put the coordinate and literally move it down 2. Okay? Now, is our horizontal asymptote still at 0? No, we have a vertical shift, so it also gets bumped down 2. So our asymptote, if I can write, is y equals -2. Our domain will always be all real numbers, but then since our asymptote changed, our range is also going to change. Our range is now -2 to infinity. What's really nice is we went through all of this work with our transformations of functions. Every time we talk about a function, those transformations remain the same. So all that work we did in chapter 1 with reflections and shifts and stretches, okay, those stay the same. When we talked about our parabolas in chapter 2, our exponents today, our logarithms tomorrow, okay, our trig functions when we get to next semester, all of our transformations are the same. Okay, so let's change our, let's talk about the number e very quickly. The number e was e. E is called the natural base. You might also hear it called Euler's constant, E-U-L-I-E-R, Euler. He named a number after himself. Okay. E is an irrational number, which is approximately 2.718281, blah, 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 blah. It's irrational, so it goes on forever. But it's very important for us. Euler's constant is very important. Oh. How do you know it's irrational? Well, so there's a pattern. There is a pattern that, okay, so it's not a pattern with the numbers, but, oh, they don't have it in here. Okay. What I'm going to let you do is I'm going to let you start copying down this formula here for compound interest. Do you remember this? Compound interest? Okay. Start writing this down and I'm going to get you the definition of E. Okay.
Yeah.
I wouldn't say like messing around getting bored, but like messing around doing his research. Right? He was researching mathematical concepts.
I don't know that that's what you did that. I would like 18 hours in every
So compound interest, where do we find compound interest? Like what kind of examples? Money. Okay, real life, right? Banking, car loans, all sorts of things, okay? A is considered the amount after time. I should say time is in years, okay? N is the number of times compounded per year. So if it says compounded monthly, that would be 12 times a year. Compounded annually, that would be once per year. Your rate needs to be a decimal. So if they say 20%, you need to write it as 0.2. Okay? And then your principal, that's how much you start out with. Okay? Now, the more you compound, is it going to help you make more money or less money? Okay, if you are saving money, compounding more often will help you get more money. Okay, if you have a loan, compounding more means you're going to have to pay more money. Okay, so if we think about compounding and we want to keep compounding more times per year, we can do what's called continuous compound, where it's always recalculating, okay, as opposed to just so many times per year we're calculating this interest. Continuous compound, somebody already said it, what is it? Hurt. Everything stays the same, we just have e to the RT. Everything stays the same. We are just compounding all the time instead of so many times per year. Okay? So if you're presented with two problems, one has compound interest so many times per year, one has continuous compound, this number should be higher because it's calculating all the time. Okay? So to finish out class, we are going to talk about this. Okay, and I want to help you with your calculator here. A total of $12,000 is invested at an interest rate of 9%. Find the balance after 5 years if it's compounded quarterly and continuously. So this is what I would do if I were you. $12,000 is invested. What is that? P. So write P equals $12,000. Okay? Annual interest rate of 9%. Annual interest rate of 9%. R is 9. R is 0.09. Find the balance after 5 years. Means times 5. So A equals P. 1 plus our rate over N, is that correct? Okay, so our rate over n, and it gets compounded 4 times per year. So we have to take that rate and cut it into those 4 different times we recalculate. And then we raise it to the NT. How many decimal places are you going to approximate to? 2, because we're dealing with money. Right? When you put this into your calculator, please do not punch things in and hit enter like 5 different times. You have a nice calculator. Please use it to your advantage. Okay? My suggestion to you, when my calculator decides to open, come on, calculator. Okay. We have 12,000 times, type it in exactly as you see it. 1 plus, is it 0.09? Divided by 4. Parentheses, raised to the 20th power. There is no need for you to type things in individually. Just type it in all at once. You can do it. You can do it. Okay. So we have $18,726.11. If we're talking about PERT, we have 12,000. E raised to the RT. $18,819.75. E is the third button from the bottom on the very left side. You have to press second. It should have a natural log with it. Okay. Now, I will say, I just handed you your gold sheet. Juniors, we're going to be doing some ACT stuff in the library, and so next week is going to look different, and things are going to get bumped a couple days. So don't put these like in your calendar quite yet. We're going to have a quiz on Friday for sure, and then next week things get changed up, okay? Okay, think about if you want to retake and come in tomorrow. Ready to talk to me about it.
Thursday.
Yes.
Yes.
Oh, yeah.
Not gonna be on Friday. Is that what I do?